Hello everyone, I am Aman and today we are going to learn about one of the most important class of algorithms, divide and conquer. These class of algorithms have given rise to one of the most functionally important concept of programming languages known as recursions. So one of the most basic example of divide and conquer algorithms is known as binary search. So I will formulate the problem as follows. So assume that you have given a sorted array of n elements. So what do I mean by sorted? Sorted means that the elements of the array are arranged in either increasing or decreasing order. So in more mathematical terms, if I is less than j, that implies that ai is less than ej. Now the given problem is that you are given a key k and you need to find whether that key k exists in the array or not. So what can we think of the naive solution as? So the naive solution for the problem would be to actually go check whether k exists in the array by iterating through the complete array. So what do? We iterate through the array and we check whether k exists. If we find k, we return true, otherwise we return false. So, but as you can see that this is something which would iterate through the complete length of the array. So we had a property of the array that the array was sorted, but did we anywhere use the fact? So the answer is clearly no, we did not use the fact that the array is sorted. So what can we do so that we use the fact that the array is sorted and can improve in the number of steps that we take to find the array element k? So I'll give you an intuition of how binary search actually works. So suppose you have to search for the word mango in the dictionary. How would you do about it? You would first go to the letter M, then you would search for all the elements that start with M and begin with A. Then you will go with M-A-N-G, and at each step you are just actually eliminating half of your search space. So in a similar way, the binary search actually works. So I'll give you the formal algorithm. The formal algorithm is you take two pointers, L and R, you set L to 0 and R to the length of the array. Now, if L is greater than R, you terminate the search and return unsuccessful. That means that the element was not found. Otherwise, you find the middle element of the array, which is the L plus R by 2. In the next step, you actually compute the middle element of the array with the key that you want to search. So if it is less than key, that means that the element you are searching lies in the right half of the array. So you set L to M plus 1 and then go back to step 2. Otherwise, if the middle element of the array is greater than your key, that means that the element that you want to search for is in the left half of the key array. So you set you decrement the R pointer to M minus 1 and go back to step 2, and you keep repeating it until you reach the condition L is greater than R. And the base case is where if you find the key, that means that search is done and you return the index name. Let's look at an example of binary search. So consider this array 1, 3, 5, 7, 11, 13, 17, 19 and so on. As you can see that the array is in increasing order, and suppose we need to find the key 37. So how would you go about doing this in a sequential search? So you'll first match 37 with the first element, then you'll match it with second element, then you'll match it with the third element, then you'll match it with the fourth element, then the fifth, and you keep doing it till you find 37. So as you can see that in this case, this is very slow. So instead, let's look at what binary search actually does. So binary search would actually first set low to 0 and high to 16. So that makes mid to be 8. So then it compares the 8th element with 37. So as you can see that 37 is greater than 23. So it sets the low value to 9. Now we continue. It sets the low value to 9 and the high value to 16. So the mid element would be 41. It says less than that, so it sets high to 11. Now it again iterates through this and so on till find that the 37 is placed at the element 11. So as you can see that the binary search takes about 3 steps and the sequential search takes about 11 steps. So more formally, if you state that if there are n elements in the array, the binary search of that element would take about log n steps and the sequential search would take about order n steps. So I am assuming that you know a little bit about the big O complexity If not, you can actually look up in the further tutorials for the bigger complexity. So binary search is order log n and sequential search is order n, which is a great speed up. So the previous example of divide and conquer actually worked on the following assumption that the array was sorted. So now the fundamental question rises is, what if the array is not sorted? So we'll look about some of the algorithms that can actually make an array sorted. So the first and the foremost algorithm that is used in divide and conquer to sort an array is quicksort. So the problem is as follows. So suppose you have an input array A of n elements. So this time the array need not be in sorted order. So because the problem itself is to sort the array or array of numbers in either increasing or decreasing order. So what could be the intuition for this? The intuition for divide and conquer would be to divide the array into two subproblems and sort each of them recursively. So we'll see this first with a little bit of animation and then we'll formalize the algorithm. Let's look what quicksort actually does with a small animation. So try to understand the algorithm with the animation, but never mind if you don't understand, I'll formalize it later. So as you can see, so now I'll try to sort this array. This is sorted. Now it will try to sort this part of the array. And here we have the complete sorted array. Okay, so now just look at the algorithm for quicksort in a more formal way. So what do we said? We said that quicksort actually breaks the problem into two subarrays. So what do? We actually divide the array into two smaller subarrays, the low elements and the high elements, and then we recursively sort the subarrays. So this is the basic idea. So first we look at how we actually divide it into small arrays. So first we pick up an element, say pivot from an array. So this can be any element from an array and we generally select a pivot randomly from an array. Now we partition the array into two parts. So the partitioning is actually based on the way that you reorder the array so that all elements that are less than the pivot come before the pivot and all elements which are greater than the pivot come after it. And the equal values can heuristically go to either way. So this partitioning is quite simple, where you can just do it by setting up a pointer in the beginning and setting up a pointer at the end, and you keep checking it each time. And if you encounter a mismatch, you actually swap the elements. Now you will recursively apply the above two steps to the two subarrays, which have the smaller values than the pivot and which have the larger values of the pivot. So using this way, you can actually sort the two subarrays, and then since merging these two subarrays is quite trivial, you actually have two sorted subarrays and the pivot in between, where the array to the left of the pivot, all the elements are less than the pivot, and array to the right of the pivot, all the elements are greater than the pivot. So now let's look at how quicksort works on the example that we have seen before. So consider that we select 3 as the pivot. We set one pointer low to 6 and the other to 4, and we keep moving it and we partition the array into two steps. So whenever we see that there is a mismatch, we actually swap the elements of the array as so. So now you have two arrays, 2 and 1, and 5, 8, 7, 6 and 4, where each of the elements in this array 2 and 1 are less than 3 and elements in this array are greater than 4. Now we actually repeat the same thing on this small array. So this time we selected 1 as the pivot, and now we swap the elements. So now we have this array 1 and 2 sorted. So now we are going to sort this smaller array. Sorting this smaller array, we supposedly choose 4 as the pivot. So now we could just swap the elements in such a way that elements to the left of 4 are less than 4 and elements to the right of 4 are greater than 4. Now we'll again sort this part of the array where we select the pivot as 6. Now again we repeat the same step. we pivot the array in such a way that elements to the left of 6 are less than 8 and to the right of 8 are greater than 8. Now, as you can see that the algorithm will now sort this part. This is sorted, this is already sorted, and this is already sorted. So finally we have the complete sorted array. So let's understand how this algorithm performs in the number of steps, or more precisely, let's look at the analysis of the runtime of the algorithm. So let's say that the algorithm actually chooses a pivot and it divides it into two parts, the left sub half and the right sub half. So consider that the left sub half is of size p and the right sub half is of size q, where p plus q is equal to n minus 1. Then we have the following recurrence relation, Tn is equal to Tp plus T of n minus p plus order n. So I'm assuming that you know a little bit of recurrence relation. If not, please find a link to one of the tutorial of one of my friend who actually has a good tutorial on recurrence relations. So if you solve this recurrence relation, you will see that the best case would be when p is n by 2, which is order n log n, and the worst case would be order n square. So as you can see that the algorithm does not always performs good. Sometimes it also performs bad in the case as we will see later in the video. So now let's consider the worst case partition. So consider the array where you choose an element and one region has only one element and other has n minus 1 elements. So this is actually a very bad partitioning of the element because you are actually just reducing the array size by 1. So like we said before that we actually divided into two sub-problems, and the best case would be when we have actually two sub-problems of equal sizes. But now since we have just reduced the size by only 1, so this is the maximally unbalanced case. So consider the case where you have an array of size 1, you divide it into left part of array of size 1 and the right would be of n minus 1. So you'll keep doing it till you actually reach the array of size 2 where you divide it into two parts of size 1 and 1. So if you see that this is a kind of a binary tree where the height of the tree is actually n. So you see that the number of steps it requires at each step is proportional to the length of the array at that step. So you'll take n, n minus 1, n minus 2 and so on till up to 2 steps. And thus if you sum all of them up, you'll find that this is order n squared. So we can work this around with using a recurrence relation too. So consider that t of n is the time taken to sort the array. So t of n would be t of 1 plus t of n minus 1 plus n. So we have the base case where you just have one array of element 1. So the time to sort that array is 1. So now if you solve this recurrence relation, you will find that t of n is equal to t of n minus 1 plus n. Now again, this can be solved intuitively using this tree or in a more rigorous form using generating functions to yield the following solution that t of n is equal to order of n square. So this is the worst case time that the quicksort would actually take, but we'll see that in general quicksort performs better, and we'll later on see what the best case sorting of the algorithm would be. So now let's look at what actually the best case partitioning of the array would be. So the best case would be that you actually divide the array into two equal parts of size n by 2. So this would be the maximally balanced tree where the height of the tree would be minimum. So consider you have an array of size n, you divide it to get two arrays of size n by 2, which you further divide to get two arrays of size n by 4. Then you further divide it to get 8 arrays of size n by 8. So at each time step you are actually spending order n time, but in this case the height of the tree would be log n, log to the base 2. So we can work this around using a recurrence relation too. So which says that substitute p is equal to n by 2 in the first recurrence relation. So you get t of n is equal to 2 times t of n by 2 plus n. Again with the base case is that if the array is of size 1, then the time to sort that array is 1. So now again you can solve this recurrence relation and you get t of n is equal to order n log n. So as we have seen that the quicksort actually can perform in the worst case order n square and in the best case order n log n. But in general for the arrays that we really encounter in practice, quicksort actually performs on an average, gives a complexity of order n log n. So in which case it is much better than the naive sorting algorithms of insertion sort, bubble sort and selection sort, which always gives order n squared time. So the next algorithm that we are going to learn to actually sort an array is merge sort. So again, the input is an array of n elements, and the problem is to sort the array in either increasing or decreasing order. So again, the intuition, since it's a tutorial on divide and conquer, would be to actually divide the array into two different smaller arrays and then later on merge them. But this kind of division is a little different from how quicksort actually divides. So we'll see this with a little bit of animation. So let's look at the animation where we again have to sort the same array, but this time using merge sort. So now let's go through the algorithm in a brief. So if you look at how actually it was being done in the animation, you actually divide the array into two equal parts. This is something in contrast with how quicksort actually performs, where the parts of the two sort problems are different. But here you actually divide the array into two equal halves. So what we do is we actually split the array into two equal sized parts, and then we recursively sort these two parts. So now the problem is that you have two different sorted arrays and you need to merge them up. So these sorted arrays are merged in a very simple way, where you pick the first element that is the minimum of the two. So this merging can be done in linear time, and thus the worst case complexity is given by this recurrence relation. So here I'm assuming that you know a little bit about recurrence relation. So consider that t of n determines the time that is taken to sort an array of size n. And since we are dividing it into two smaller arrays of size n by 2, t of n by 2 is the time required to sort two arrays of size n by 2. That's why it's 2 times tn by 2. And now when you have two sorted arrays of size n by 2, you can actually merge them in linear time, which is order n. So now if you solve this recurrence by any kind of method using generating functions or anything, you will actually see that we get t of n is order n times log n, which is the same as what quicksort actually does. So we can see that merge sort is actually sorting the array in order n log n time, whereas if you actually naively sort the array, it would take about n square time. So since you get a speed up of about n by log n, which is actually a great speed up, we can say that merge sort actually performs better in comparison with the other sorting algorithms that are in place. So now let's proceed with the example once again. So you can see that you have this array 6, 5, 3, 1, 8, 7, 2, 4. You actually divide it up into two parts and make two arrays of size 4 and 4. Then you divide the first array of size 4 into two another parts of size 2. The same you do with the second array 8, 7, 2, 4 to get two arrays. Now you again divide the size 2 array into two arrays of size 1. Now, since you have divided each of the arrays into two arrays of size 1, you actually have each of these individual 8 arrays as a sorted array. Now, you take the first two elements and you actually try to merge them. So merging is simple. You take a pointer at 6 and you take a pointer at 5 and put the smallest element in the beginning and the next element after it. So as you can see in this animation, you take a pointer at 6 and 5. You actually place the smaller element in the beginning and then the bigger element. You do the same for each of these two pairs in the way that you set first pointer to 3 and 1, then you put the first element 1 and then the second element as 3. You do the same for 8 and 7, and next time you do the same for 2 and 4. So at this step we have arrays of size 2 which are sorted. Now to again merge these two arrays, you take one pointer at 5, you take one pointer at 1, and you keep merging them in linear time. So you put the smaller element in the first and you increase the pointer of the corresponding element to 3. Now you compare 3 with 5. Since 3 is less than 5, you put 3 in the beginning. Then you put 5 and then you put 6. So you have actually merged these size 2 arrays to form a size 4 array. And you do the same thing with this. You put a pointer at 2 and 7, then you compare 4 and 7, then you put in 7 and then 8. So at this step we have actually 2 arrays of size 4 which are sorted. So now the only problem left is to actually merge these 2 arrays, which is again trivial given the step that we actually take one pointer at 1 and one pointer at 2 and put the smaller element in the beginning. So again I'll put 1 in the beginning, then 2, then 3, 4, 5, 6, 7, 8 and so on. So you can see that finally you have this array 1, 2, 3, 4, 5, 6, 7 8 sorted. So we actually reduce the problem into half at each step and merge them in linear time. So now it's time to conclude our tutorial. So what have we learned is actually that divide and conquer is a very powerful technique. It is used in most classes of algorithm. So the basic idea of divide and conquer is actually you somehow have to figure out how to actually divide your problem into 2 problems of smaller sizes, and then actually you need to find a way of merging these 2 smaller sub-problems to find a bigger problem. So it is typically applicable when the structure of the problems allows breaking into sub-problems of similar type. So consider the algorithms that we have considered, like quicksort and mergesort, allowed the structure of the problem was to actually sort the array, and it was independent of the size of the array that we were given. So we can actually divide the arrays into 2 subparts, 2 sub-arrays, and actually sort them recursively. So many a times it improves the time complexity of the problem as compared to the naive algorithm. So like quicksort and mergesort on an average give a time complexity of order n log n, whereas the naive sorting algorithms like bubble sort, insertion sort, selection sort give a complexity of order n square. So we can say that divide and conquer is actually very powerful, and you should always think about a method that can actually divide the problem into 2 sub-problems. And it can, in any cases, improve the time complexity and would reduce the amount of coding that you actually need also to implement these algorithms. Some of the other popular use cases of divide and conquer are actually binary search, quicksort, mergesort, which we have studied. So some of the other difficult, not so difficult sub cases of using divide and conquer is to finding the kth smallest element. So consider the case that you have, I'll describe the problem in brief. So consider that you have an array of size n and you might want to find the kth smallest element. So note that the array is not sorted here, because if we had a sorted array, we could actually just return the kth element. The other, which is a slightly more difficult version of divide and conquer, is actually finding the closest pair of points. So assume that you are given n points in the plane and you need to find which 2 points are closest. So all these problems have various applications in various real life applications, and it is actually very useful to think about divide and conquer when thinking of an efficient algorithm that can actually work about this. So thanks a lot. This was Aman, and thanks a lot for watching this tutorial.